Hello guys, thank you for watching our sixth lecture. Today I'm going to talk about the properties of pure substances, which is chapter 3 of the textbook. So I hope you're all enjoying the course, and I'm trying to do my best to make everything simple and easy. So I hope you feel comfortable with the materials. So before I solve the example today, I would like to go to the blackboard and just take a look over some changes that I have been placed. I have placed. So in our lecture schedule, on the third column, you can see the package of 3 days, 9th, 10th, and 11th, this weekend. And we're going to cover the properties of pure substances, energy analysis in closed systems, internal energy, enthalpy, and specific heats. We're going to cover a lot of material, and they are in chapter 3 and 4 of the textbook in these sections. And the lecture notes, the corresponding lecture notes are 6, 7, and 8. The assignment number 3 will be posted at 8 a.m. Well, today, and the solution will be provided after 24 hours from this date. So let me go back to our website on the blackboard, and then in the content, if we go to lecture material, lecture videos, so as I mentioned before, we're not gonna use the Google Drive anymore. We've switched to the software, the website called Panopto. So if you click on this link provided here above each of these embedded pictures of the videos, it takes you to the video, and then you can click
Hey guys,
customize and watch the lecture. The notes number, so for this chapter 3 and 4, the notes 6, 7, and 8 with these subjects are posted. Please, this is going to be your reading assignment. Please take a look at this before you watch the lecture, although meanwhile that I'm giving you the solution and we're solving the example, I will refer to the related pages of this lecture note. And at that time, as I mentioned before, I do strongly recommend, suggest you to pause the lecture, go to the lecture slide, read it again, and recall all the material and keep it in mind. Then come back to the lecture, play, and watch the rest of it. The examples for the examples number 3, about chapter 3 and 4, are uploaded here. Since we're covering a lot of material, so I've dedicated 5 examples here. I'm not sure, I might reduce the number, or I might stay with these. I'm not sure, but anyway, so in this lecture I'm going to talk about this first one here. And again, please keep this in front of you on your screen, because meanwhile I will refer to information provided in the text of this question, and I have it here in front of me. So that's it. So let's solve that example. Here's my notebook. Okay, great. So the example number 1 says water initially, so let me read the whole thing for you, because as I told you before, you're supposed to imagine the story. So you need to, let me check this, okay, great. So you need to read the example, the question, the text at least one time before you start to solve it. So listen. Water initially at 200 kPa and 300 degrees Celsius is contained in a piston cylinder device fitted with stops. Okay. The water is allowed to cool at constant pressure until it exists as saturated vapor, and the piston rests on the stops. Then the water continues to cool until the pressure is 100 kPa. Okay. On a TV diagram sketch with respect to the saturation lines, the process curves passing through both initial intermediate, and final states of the water. Label the T, P, and little v, which is, what is it? Specific volume per mass. Values for end states on the process curves. Okay. Find the overall change in internal energy between the initial and final states per unit mass of water. Okay, and we have the answer. Great. Well, do you remember what was the first step that we need to do? Great. System. What are we gonna talk about? I don't know. Let's check the question. Overall change in internal energy of what? Of who? Water. It's a piston cylinder device, so the piston is sealed. There's no opening, it's closed, and there are stops. It's getting cooled, so perhaps the piston comes downward because I'm cooling the water, so it's gonna shrink. Okay, the piston is coming down, and it's asking for internal energy of water, and the mass is not gonna change. It's conserved. It's not gonna change. So, wow. So the pis. Oh, so the system is. Okay, great, great. Oh, the question told me, the text told me what to pick as the system. The water, whatever, which is inside the piston cylinder device. Uh, okay, okay. I know. Great, great. So, wait a minute. I'm gonna talk about specific amount of mass, right? And it's gonna be conserved, and that's it in front of me. Whatever that is inside a container, inside this piston cylinder device, is gonna be with me all the time through this solution. So I see. I'm gonna talk about specific amount of mass. Specific amount of mass. Oh, I remember that Sepper told me that whenever I'm talking about a specific amount, that it's like fixed. So it's a closed system, right? My system is closed. The content of piston cylinder is closed. It's not going to change. So the system is closed. No mass transition. So if it is closed, so does it mean that it's control mass, not volume? Because he told me that when we talk about control volume, it means the system is open and we have like kind of like a flow coming in and then leaving the system. So it's control mass. Yeah, it's control mass. And oh, and the boundaries. And the boundaries are real. It's closed. So there should be like a real um, limit for the mass to leave the system, like a barrier or something. So my system is gonna look like um, kind of like this. It's like as I see in the on the figure, I have these little tiny stops, And then here's the piston. Okay, and it says it's cooling, right? It's water because it's perhaps it's like shrinking, right? So it comes downward, it moves downward, and these guys are stops, and this block is the piston. Okay, and the contain the whatever that is inside here is the system, right? It's closed. Okay, and so it's cooling, right? So how do I cool a system? So I take out the energy out of it in shape of what? So when I cool, let's say I put it in a refrigerator, so I like kind of take out the heat, right? It's like kind of Q in like parameters. So it's Q is heat, right? Why? Because I'm cooling the system. Okay, I see. Now, what am I supposed to do? Uh, let me check the example again. Oh, okay. We want to draw the TV diagram. It's asking for diagram for the process. So it's a process, like it consists of like different processes, like 1 to 2, 2, 3, 3 to 4, some specific checkpoints. So these checkpoints are called, so we need to, before I define this process, I need to know exactly what are the checkpoints that I'm like passing through them. And these states or like checkpoints are particular moments oh I forgot to oh my god particular moments that I'm sorry, I forgot to change the audio recording, so the quality of like the voice might not be as good as before. I'm sorry about it. uh, Particular moments that an event um, ends or starts at. So in this case, I know that I need to draw the TV diagram. Therefore, I need to define my process. And a process consists of different states, different checkpoints, these different points, right? And so, so I need to define those points before I go through this solution. So the process states are one, the initial state, well, before I write this for you, you or suppose you need to, from now on, do exactly and take these steps that I'm gonna go through, because this is the trick. This is my experience, right? And I'm giving this to you. I know that by this way, by this kind of like algorithm or like point of view, we will be able to easily kind of like digest this question and then be able to solve it, because in thermodynamics there are a lot of information in the question, provided in the question, and we will be like kind of lost in it. We don't know where to start from, and then like which direction to go, find what and then what and then what. The order of these sub questions will be uh, uh, kind of like vague, that it's not quite clear. Anyway, so I do recommend you to take these steps as I'm exactly in the same way that I'm doing this. So the first initial state is, so you need to specify the material. Material is water. Sometimes it's like another chemical stuff, right? It helps us to know exactly which table to go through. And then the question says water initially at 200 kPa. So P1 equals 200 kPa and 300 degrees Celsius. So temperature is 300 degrees C. So, okay, great. This is what it's telling. It's contained in a piston device fitted in the stops. The water is allowed to cool. Okay, so now the question passed the first initial state. Okay, so this is all I know. Then the second one, the intermediate state is, well, what is the material? What is like what is it? What's the state? It is the water is allowed to cool at constant pressure. It's talking about the process. I don't care. I'm just focusing on the state. Until it exists as saturated vapor. Perfect. This is what I'm looking for. Saturated vapor. Please pause this lecture and then check the pages 1, 2, 3, 4, 5 of the lecture note number 6. Thank you. Well, so I assume now you're back. So the piston, and it says so exists as saturated vapor, and the piston rests on the stops. So from now on, the piston is not going to move anymore. It's stopped. So, and then the piston stops. So at this moment, stops. Remember, I told you here, I defined it. Particular moments that an event ends or starts at. And the third state is final state. So what's happening then? Then the question says, the water continues to cool. Okay, this is the process. I don't care. Until, again, see, until is like a sensitive, is critical word. Because like then after until, it's going to say about specific conditions of that particular moment. Until the pressure is 100 kPa. So okay. What is the material again? Is it talking about saturated something or like no? So it's just water again. Because when we say water, we don't know if it is saturated liquid, saturated vapor, it's subcooled, it's superheated. It's just water. It's like H2O. That's all we know. H2O, just a molecule. Okay, don't judge based on this word, unless like, well, I guess I might solve another example that I'll tell you later in another lectures. Anyway, and then it says the pressure is 100. So P3 is 100 kPa. Okay, great, great, awesome. So far we summarized everything except process path. Well, so far I was focusing on those checkpoints and I didn't care about like how do I get to that point from like checkpoint number 1 to checkpoint number 2. What is happening? Is it like the pressure is constant, piston doesn't move, is adiabatic, like Q is 0, or there's no work on the system, or like if the temperature is constant through that see, we have a lot of a variety of all different processes, right? And we need to specify that uh, how do we like travel from one checkpoint to another. We have 3 states, so it means that we're going to have 2 processes. The first one is from checkpoint 1 to 2, state 1 to state 2. And again, let's go back to the question. It says, the second sentence, it says the water is allowed to cool, so it's cooling, at constant pressure, and the pressure is constant. Which means in like parameters means that, so I'm like traveling from point 1 to point 2, so P1 equals P2. And if you go back to the summary, we know that P1 is 200 kPa, which means that P2 should be 200 kPa as well. And then the second path is from point 2 to point 3. Let's see what is happening. Then the water continues to cool again, so it's the second path of cooling, and until the is there any specific condition that this process is going through from point 2 to point 3? Please, and let me check the previous sentence. The water is allowed to cool at constant pressure. No, that was the first path. Until it exists as saturated vapor and the piston rests. Oh, and the piston rests on the stops. So from now on, the piston is not going to move anymore. So the piston does not move in this path, in this process, point 2 to point 3. Okay, so piston doesn't move. Which means that the volume of my system is constant, right? Oh, so these are volumes. And do you remember that from the beginning we assumed that our system is control mass? Remember? And control mass means that the mass is not going to change. It's like we focus on some specific amount of mass, and we're going to judge on that mass in the whole example, right? So we're talking about a specific amount of mass, and that's it. We stay with all these molecules, and we talk about like each of these molecules. There's no flow. There's no new materials coming into our point of view. It's the same old material that we were talking about, right? So it means that the mass is the same. M2 and M3 are the same, right? So we have something called specific volume, which is defined as the volume per mass, volume over mass. So according to these definitions, V2 over M2 equals V3 over M3, and these two portions are basically the little v's, specific volume per mass. These are volume per mass. Why do I care about specific volume per mass? Because if you go to these tables here, let me show you. Here it says saturated liquid, saturated vapor, and they're all little v's, specific volume. See, so all these tables are provided with specific volume, and this is what we should look for, right? So meanwhile that we are solving the question, we are going to work with specific volumes, not just the volumes itself. Now the next step that I want to teach you is that you need to, so let me say something here. So far we have specified all here the path between three different checkpoints. We know exactly what's going on, and then here we have talked about those checkpoints itself. So now it's like kind of like a long story, and meanwhile that you're doing your homeworks or like in the exam, you don't need to write all these. You can just you see them in the text, and then you think about it, you have it in your mind. So this is like how to teach, you know. So but the thing that you need to do is just a simple table. Okay, so let's write this table. So this table is like, so you say you write point 1. We are gonna repeat writing these table on and on again, like too many times, so many times in all these examples. Oh my god, it's difficult to write it straight line. Okay, that's good. And then point 2, another line, and point 3. States, checkpoints, and then the summary. So here it said P1 is 200 kPa. What else? T1, temperature is 300 degrees C. Okay, and do I know anything else? No. If you just go back here, initial state P1, T1, and then water. That's all we know. What about point 2? Oh, let me go back there. Okay, what about point 2? Oh, it's like piston stops, and then saturated vapor. Okay, so here I'm talking about saturated vapor. And do I know anything else? Oh, here, P1 equals P2. Okay, which means P2 is 200 kPa. Okay, and one more thing here. The second path, we proved that a specific volume is constant through the second path. Therefore, V2, what? So little v 2 equals little v3, and same here, v2 equals v3. Just to keep in mind, makes it more simple. And it says that at the very end the pressure is 100. So P3 is 100 kPa. Awesome. I guess we don't know anything else. That's all we know. Yeah. Now the solution starts. So at point 1, we have water. We need to go. See, now I told you before. This is why I told you that the matter matters. Like, it's important because then I know which table to go to. So table A5. It's in SI units, not in English units, and find the saturated temperature. At the corresponding pressure at P1. Why do I do this? Because you remember that I said here at point 1 we don't know the condition of the water. We don't know if it is subcooled, superheated, or vapor, like saturated vapor. Well, actually we can guess. It's like tricky because from point 1 to point 2 it says that we are cooling the system, and at the end of the process we get to the saturated vapor. So we expect it to be a superheated vapor, then it cooled down to a saturated vapor. If you check the page 14, then you can read more about it. So at P1 kPa, so the table says that the saturated temperature at 200 kPa is, let's go to the table. So here's table A5. Let me zoom in. Okay, and on the very left column we have all these saturated pressures, and the pressure that we're talking about is 200. So this is this row, 200. Oh. Okay, and at this pressure, the saturated temperature, here's the second column, saturated temperature on top. It says 120.21. 120.21 degree C, right? And we know in our table, we know that T1 is 300 degrees C. So if you compare these two temperatures, you'll see that T1 is 300 degrees C, which is larger than T saturated at that pressure. Therefore, we conclude that water is what? Is superheated, because the temperature that water is at this point T1 is much higher than what it's supposed to be if it was saturated. So now it's not. So it should be like warmer than the saturated vapor. So it's like a very hot vapor, very like warm vapor. So water is superheated. Sometimes I get like excited with like what I'm talking. Superheated heated. Then we need to go to another table, because this is all about saturated table. So we need to go a little down to A6 here. A6 talks about all the properties of superheated water. You can see at the top, it's about superheated water. At this, each of these squares, these blocks, is at that pressure on top. Here is like the very up left one, P equals 0.01 megapascal, and then 0.5. We are talking about 200. So 200 is 0.2 megapascal here. And then the temperature is 300. So this is the information that we're looking for. So now we know everything that we need to know. Again, please hold on and wait. Wait a second. We are looking for what? Don't get lost in the question. Let's go all the way up and look at our question. Overall change in internal energy. Internal energy, internal energy. Internal energy is U. And in the table, U is there, here. So it's like the third information is 2808.8 what? Kilojoule per kilogram. Oh, so therefore U3 equals U1 equals 2808.8 total 8 kilojoule per kilogram. And please do this. Go back to your table and write it in red, whatever that you have discovered. It's super heated, and internal energy is 2808.8 kilojoule per kilogram. Don't be lazy and write the unit. Please, 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 please. Helps a lot. I have this experience that I lost point just because I hesitated to write the unit. The next point, again, the material is water. What is the table? What is the famous table that we need to check in the beginning always? For water, A5. Let's go to the table here, our table. We know that the vapor is at this point we have saturated vapor and pressure is 200, and we know that all the information about saturated state is in table A.5. At that pressure, which was 200, again, these are the information that we are looking for. And pay attention that we are, at this point, we are actually on the saturated state. So like the temperature is, so if the pressure is 200, it means that temperature is that. It means that specific volume like VF, VG, UF, all internal entropy, everything is there. Because we know specifically what point we are at. We are at saturated state at that pressure. That's it. So all these informations are what we are interested in to know. So at point 2, question says that we have saturated vapor, which means that the quantity X equals 1. Please stop here and then go check these pages. 10, 12, 13. And according to the table that I showed you before, we know that oh, wait a second, let me tell you something. So I have a lot of information here to pick. Which one should I pick? Which one is helpful for me? If you go, see, I told you, this is why I'm mentioning and I'm emphasizing on this table so much, because here we wrote a little note for ourselves that V2 little v equals V3, and this is the link that helps us to somehow jump from this point, the information, get all the information from here, and then go to the other side and use it there and find whatever that we're looking for. We're looking for U, right? So it means that we need to pick the values for specific volumes at point 2. So I'm interested in V little v, right? I'm not interested in entropy. I'm not interested in enthalpy. Why? Because I know that little v, a specific volume, helps me to pick it and make it equal to V3. It means that I jump to point 3, and at that point I can find internal energy. This is the trick. This is the trick, that why do I pick little v? Because it helps me. Because if I pick little v at this pressure and it's saturated vapor, according to the table, it is 88. You need to have a table in front of you, please. 58. This is all I know about point 2. Just the pressure and V2 equals V3. That's all, and the quality. That's all I know. This is all I know. All these 3 things. And now to be able to go to point 3, I can take advantage of the fact that I know V2 equals V3. So now I can continue and go to point 3. At this point, the material is water. Great. And again, according to table A5, I know that I have the pressure in my table, which is 100 kPa at that point, point 3. So I know pressure is 100 kPa. And I forgot to go back to my table and edit and say add the information that I discovered, that V2 equals, this helps on your exam. Then you have all the information just at specific spot on your paper, and you can refer and save time. You do not need to look for what you have calculated. Everything is here. So with this information, check the properties on the table A5. You can check it down. That I'm writing properties. So here I'm not sure. It's just water. See, I don't know if it is like saturated what. It's just H2O. So I need to know that either if I am like subcooled, saturated liquid, or it's a mixture, it has like quality X, which is like something in between 0 and 1, or it's 1, which is saturated vapor, or it's superheated. We need to judge. And all we know is just a pressure and a specific volume. That's all we know at that point. So if I check the values for saturated liquid and saturated vapor specific volume. At these points, saturated liquid and saturated vapor, which is like V3F and V3G at 100 kPa here. They are 0.001043 and 1.6941, and the units are meters cubed per kilogram. So then I realized that, V3 that I have calculated before, which was V2, is in between saturated liquid and saturated vapor, which means that I have a mixture of two different phases, the liquid and the gas. So according to the definition that you have checked before, we can calculate the quality of this mixture, which is defined as V3 minus F divided by Vg minus Vf, which is 0.8858 minus 0.001 043 divided by 1, which is 0.52. And once again, what are we looking for? Internal energy, the difference. So U1 we calculated before here. See U1 in this table. And we need to know U3 because we are looking for overall change in internal energy. So according to the equation, U3 can be calculated by this equation, which is UF plus X3 UFG. And if you go to the table at this pressure, you know that internal energies are UF and UFG, these two numbers, at 100 kPa, and the unit is kilojoule per kilogram. Therefore, got it. This was what we were looking for. Oh my god. So that is difficult. Delta little u per mass in the process 1 to 3 equals U1 minus U3 equals what we just found. Ta-da! Awesome. That's it. We spent, oh my god, 50 minutes to just find this. And then the diagram, it is easy. The diagram is easy. Go to these pages 4, 7, 8, and 11, and then come back. And then, oh yeah, at this one 7, it says that the saturated line is like in this shape. So here's my T axis, and here's my little v axis, and the saturated line is this shape, right? And I know that here under the curve I'm at saturated liquid vapor mixture, and on the left it's subcooled, and on the very right it's superheated, right? And then once again, we need to start with the information in this table. At point 1, it's superheated, so it's very, 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 very right. Right? I'm sorry. Hold on a second. So we are like here. So it's like point 1. And then the process. Where is it? 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 Here. 1 to 2 here. 1 to 2 cooling, constant pressure. And according to the graph on page 7 on the note, a constant pressure graph looks like this. And then constant, because then it's like this is the phase change. At the phase change, temperature and pressure doesn't change, and then it continues going down. So we are on, see, from point 1, let me show you. I have summarized it here. From point 1 to point 2, we cool the constant pressure until we get to point 2, and at point 2 here we are at a saturated vapor. This is again why this table helps. So at point 2, we know that we are on this curve, on this black curve, right? We are, let me do something here. So here's point 1. And then we know that meanwhile that we are going through point 1 to point 2, we are on this curve because the pressure is the same, pressure is constant, right? And then we get to this line, which is saturated vapor, and that's it. There we are, point 2. And then from point 2 to point 3, as we summarized before, we know that it's cooling and the piston does not move, right? So what is constant? Little v. Specific volume is constant. So it's just a straight line coming down, downward. Just like this. And somewhere here is an arbitrary point, because it's like this graph is arbitrary. So then at point 3 again, we are somewhere on this line with this curve, and that's it. Point 3, point 2, point 1, and this is the direction. And this is V3, right? Oh, sorry. I mean, like, yeah, V3 at X3. You remember, it was like 0.5, so it should be like in between 0 and 1, like somewhere here. But anyway, so it's like qualitatively. And then we mentioned that these two dashed curves are P3. This is constant P, and then this one is again P1, or yeah, point P1. Constant. This was all that I wanted to tell you, and I hope that it helps. I will see you in the following lecture. Thank you so much.